We're going to go ahead and do electric fields now in this video. I will try to keep it a bit shorter than I really like to talk about the subject. It's one of my favorite ones. But anyway, let's go ahead and figure out why are we doing this. What's the point of this? So let's say we had a charge here, some big hunk of charge. We'll call it charge Q, and we have it sitting here. And then over here we've got some other chunk of charge. Let's call it Q2, Q1, Q2. And if we wanted to calculate the force between these two, we would do Coulomb's law. We'd do F equals K, we'd put in Q1, Q2 over R squared, and we'd go through and work this whole thing out where this is R, it's the distance between them, and do all that stuff, and we work it out. But now let's say we came in and we removed Q2 and we replaced it with some other kind of charge, Q3, right? Then what we'd have to do is go in and do F equals K Q1 Q3 over R squared. Okay? And then we removed Q3 and we put in some other charge, Q4, and we've got, again, F equals K Q1 Q4 over R squared. And so every time we change this charge out at that location, we have to keep redoing all of Coulomb's law. But if you notice, the only thing we're changing is this Q, which means this part in here, this K, Q1, and R squared, we're putting it all at the same location, so R isn't changing. K is a constant. We're not changing Q1 out. So this part right here is the same, which means I could write each of these out as K Q1 over R squared times this one times Q2. This one would be K Q1 over R squared times Q3. And this would be K Q1 over R squared times Q4. And if you look, put parentheses around this part right here, the part I had circled before, it's not changing. So if I go ahead and just multiply these numbers together, right, if I go ahead and do K Q1 over R squared, I can just get some number, and once I have it, I can just take that number, whatever it is, let's call it E, and I can multiply it by Q1, and that'll give me back the force. And I've got that number, same number E, and I just multiply it by Q2, and I've got the force. And I take that same number E, and I multiply it by Q3, and I've got the force now. And so what I've done is, instead of redoing the whole K Q1 Q2 over R squared, K QQ over R squared, K QQ over R squared, I just did K Q over R squared once, called it E, and then whatever charge I put in this location, right, I just multiplied that, whatever number I got, because I was keeping it constant by it, and suddenly I've gotten the force. And if I wanted to do a fifth one, change this out and put a Q6 there, Q5, Q6, Q7, Q8, Q9, all I'm doing is just taking this number that I got and multiplying it by whatever charge I put there, Q5, Q6, Q7. As long as I put it at that same location and Q1 doesn't move and Q1 stays the same, then this works. And so let's go ahead and call this a nice little math trick where we, instead of reworking the whole problem out, we work out most of it ahead of time, and we're going to call that that value E, just like I put over there. It is a vector because this Q is not a vector, it's a scalar. It contains no information about the direction. So if this is a vector, this is a vector, this is a vector, that means the information about direction must be contained inside E, since these Q's over here, Q1, Q2, Q3, Q4, Q5, they can't have any direction information in them because they're scalars. So the information still has to be contained in there, and what it is essentially is K times some charge Q. I'm going to make it a lowercase q because we're used to doing point charges, so Q over R squared. And we're going to call that the electric field, okay? That's what we're going to call it, and that's our first equation for it. Well, how in the world do we ever measure this? How do we get this value? We go out in the real world, and we've done this, and we want to measure this value. So this equation here tells us whatever E is, and this is produced, this is E, the E value produced by this Q. I'm not putting a 1 or a 2 on it because it's the only Q in the equation. So this is a charge creating this electric field thing that we just made up, okay? Really just a math trick to get our our computations reduced. So we've got it produced by this Q, and it's got a direction and all this kind of stuff, and we'll talk more about which way the direction is in just a few minutes. But how do we, if we walk out into a situation, we come across something, how do we actually measure what this is? Can we actually come up with a value for it? Because how would we do it? And what we're going to do is we're going to do something called a test charge. Basically, what we're going to do is pick a charge that is so small, it's basically unnoticeable by this Q that's creating this E here. And even though this E is a mathematic trick, I'm gonna encourage you, and the more I talk about it, to encourage you to think of this as something that is real, like a real thing there. So how do we measure this real, do quotes, real thing? And the answer is we're going to use a test charge. We want to put a charge near this Q. So what we're going to do is take out Q4, and what we're going to do is put in there a charge that is so small, tiny little point charge, that it being there or not being there isn't noticed by this Q1 here. Q1 doesn't notice. Think of it like if we had a star, like the sun. Well, the sun notices planets. If you put a planet there, the planet's going to make the sun move. All right, so if we put a big charge here, it might make Q1 move or shift around, which changes our situation. It would change R. It would either push it away or pull it closer. So what we want to do is put something small that it doesn't notice, like putting a basketball around a star. The star's not going to notice the basketball. Yes, you could argue it's going to move it, but it's going to be such a small amount, we're not even going to be able to measure how much it moves the star. It's just the star does not notice if the basketball is there or not. And that's what we want here. We want a really small test charge that allows us to put it there, look at what force is on that test charge, right? And so what we'd get is F with our test, the force on our test charge would be K, whatever our charge was, Q, times Q test over R squared. So this is the one making the charge, right? So if I wanted to, just to make this a little more clear, this would now be just what I'm calling Q. All right, so we have this, we have our test charge next to it, and then we have this R squared. We go through, we measure it, and then what we do is divide it out on both sides. You divide both sides by this test charge, and you've got K Q over R squared. That's all that's left once we divide that test charge back out. In other words, we put it there, we measured the force on it, then we removed it, and look at what we're left with. This is obviously just K Q over R squared. That's that electric field. So we put it in, and then we subtracted it away. Division is just repeated subtraction. It's just a way for us to subtract it back out. So we divide it back out, and there we go. We've got this electric field here, all from this little test charge. So that's how we would measure it using a test charge. So we've got this equation here. The other equation that goes along with it is basically this one right here, where we've got F equals EQ. Once we know E, we can get the electric force by just taking whatever E happens to be at that location and multiplying it by whatever Q we put there. So in other words, what we did is we put this test charge here, we measured out what this electric field was, or what the force was on this test charge. We removed the test charge, and now what we can do is put any charge we want there. We can go back in, put a charge in. Doesn't matter what charge we put in, whatever Q we put in now, call it Q new, whatever it is, we're putting it there, and we're putting that here, and we're getting what the force would be on this charge. So this equation tells us the electric field produced by this Q. This equation tells us the force that would be on another charge that we put near the charge that made this electric field. I know that's kind of a bit of a tricky thing to think your way through, but this one is a charge producing an electric field. This is the force on a charge that is put in the already produced electric field. So this is force on Q from the electric field E. And how does this electric field E get made? It gets made through this equation up here. This makes electric fields. This is an electric field actually producing a force on something, okay? So that's our two big equations there. And that's our E field. Now, so far, we did this for one little spot. We went right there, and we did it for that one spot. But what happens if someone brings and puts a charge over here, or over here, or over here, or anywhere like that? Well, that's where this name field comes in. Basically, what we want to do is take a little test charge. So let's go back to this being a test charge, right? And we're going to take this test charge and we're going to put it a whole lot of places. We're going to put it here and here and here and here, and we're going to put it everywhere all over. Right? Put this test charge all over and test everywhere, all around in space. And everywhere we test, we pretty much want to, we can't really do this in real life, but in theory, and we can use math to come up with answers for this, we're going to go to every single point, we're going to put Q there, and we're going to get some electric field vector pointed somewhere. And then we're going to the point next to it, and we're going to get another electric field vector. And then we're going to go next to it and get another electric field vector. And we're going to go through and we're going to do this at every single point. And if we get real far out, the electric fields are going to get weaker because it's 1 over r squared as well. It's going to reduce and it's going to get weaker. And we're going to have to do this at every single point. Now you can see that as I start drawing in all these vectors everywhere, this is going to get to be a mess. But this is what makes it a field. I don't have to draw in every one. I'm going to show you how to draw them in just a minute. But the idea is it's this whole field, like you go out into this field and there's a blade of grass everywhere. You go out into this field here, and in every point in space, you go to that point and there's some electric field vector there, and you've got a direction and a magnitude, and it's some electric field vector at that point. So if you know the electric field at that point, you go there, which we can calculate using this equation. We calculate what the electric field is at that point. Then we take that electric field, we can put a charge at that point, multiply it by that electric field, and we know what will happen if we put a charge there. We know if it'll start moving away and how quickly it'll move away, or whether it'll attract, or what it will do. Okay? So this is just lets us kind of do a whole bunch of the problem all at once, and then we can just very easily swap it out and change it with minimal disruption to what we're doing. Okay? Now, this electric field, I said, again, wasn't a real thing, but now let's talk about how we're going to draw it. And when I show you that while we draw it, it starts to look like something that's real, that you probably have some decent experience with. So first off, what we're going to do is we're going to draw electric field lines. So electric field lines, all right? This is how we're going to draw them. And we're going to have a couple of rules. Rule 1 is that the number of field lines, the field lines, right? Field lines point out of positive, and they point in, so one's out of positive into negative. Okay? And then the only other part is they go into negative or to infinity. And that'll make sense when we start drawing them. The second rule is that the number of field lines leaving a charge is proportional to the size of the charge. The bigger the charge, the more field lines it's going to produce. If you have twice as much of a charge, then it's going to push twice as many lines out, or field lines out, as one of half as much charge. Another way to think of this is that the closer together the lines, the stronger the field. And that, again, also, I'll refer back to it when we're drawing them to kind of make these make more sense, okay? But I think these two are basically the same rule, just explained in different ways. And then the last one is these lines, these field lines, do not cross, okay? They're going to add up. Any places where they would cross, they're going to add up such that they don't cross. So let's start by drawing a first simple one. The best way to learn this, I think, is just by drawing them. So let's start with a little positive charge, and I'll show you what the electric field around it would look like. And it's going to look like this. It's going to be a bunch of lines pointed out radially like a sun. Okay? Out like this. And then the field lines have a direction to them because it's a vector, and they're pointed out and away. Okay? Now if I was trying to do what I was doing above, where I was trying to put the actual electric vector at every single point, again it gets too messy. So the idea here is we can come up and follow these rules and get the same information. So for example, if I was drawing the actual electric field at a point, I would know that because of the equation, I know that the closer I am to the charge, the stronger the electric field is. So if I put this point, I'd say this is a strong electric field. And as I got further out, like I went out to this point, the electric field would be weaker. And so I'd draw a longer arrow here and a shorter arrow here. Well, I don't have to do that. I can get that same information from this. Well, first off, the electric field lines tell me that the vectors would be pointed away from this. They go out of positive, so it's pointing away. And two, it tells me that the closer together the lines are, the stronger the field. So look at the lines up close to the charge. Up close to the charge, the lines are only that far apart. As we get further away, the lines get further apart, which would mean the electric field got weaker. So instead of drawing a long arrow here and a short arrow out here, I just have the lines get further apart. That indicates that that would be the case, that the field is getting weaker as we get further away. Also notice none of these lines cross, and all of these are pointed out away from positive. Okay? What would then a negative charge electric field? So this is a totally separate situation. This isn't these two being, right next to each other. So what's the next negative charge? Isolated, just off by itself? Well, it's going to look pretty much the same. We're going to have these radial lines coming in just like this. What's it going to look like? Well, it's going to look the same, again, all these same lines, but the arrows are going to be pointed inward. So my arrows went into negative. If you look at that rule, it says here they point into negative. But then let's also not forget this, or to infinity. Look at this picture. These lines are just pointed out. Essentially, they're just going out forever and ever and ever off to infinity. So all of my lines must either go into a negative or they must just stretch out to infinity forever. Okay? That's what that means. Into negative or out to infinity. Or, I guess, they're coming out of positive, or I guess we could add this on there, or from infinity. So this line's coming in from infinitely far away and going into the negative charge, into the negative charge. They're coming from way out here at infinity and going into the negative charge. These guys are leaving out, going out to infinity, and that's that. So what about if we have then something that was twice as much charge? So let's say this was like 2 times as much charge as this one. Well, what would we do? We'd want to basically put in same kind of picture. We need it going out radially like this, so it gets weaker as we go further out. The lines get further apart. But we also want this to be a stronger field. So we follow this here. The field lines leaving a charge is proportional to the size of the charge. Well, if we made it twice as much, then we basically have to add in twice as many field lines. And this shows that this is a greater charge. But it also shows then that it's producing a stronger electric field, because the distance between the lines is less than it was over here on the other one. So I got to put my arrows in. Okay, so these all are pointed into this negative charge. But if you look at this distance between the charges here is less than the distance between the charges here. These get very far apart. These aren't as far apart. All right, so this shows twice as much field due to twice as much charge. All right, now the lines do not cross, which means we're going to have a picture where we've got charges together. So again, this is separate. But now let's put a positive charge here and a negative charge here. And the way this works is we're essentially going to have the same old fields like this, right? They go out and they point in all directions. But what we're going to do is we're going to want to think about what would the vectors at each position do? How would they add up? And then we're going to adjust our field line to this. So let's say our field lines look like this. They're going out of the positives. They're all pointed out, right? And they're pointed into the negatives here, just like that. And I'm going to switch colors here. I know I did this, kind of light, but I'm going to switch colors just so it's a little more visible, maybe over to green. And so what I'm going to do is I'm going to go to different points and look at what happens. So if I go right here, what I have is I essentially have a pretty close to the positive charge point, which gives me an electric field at that point, just doing the vector here, pointing in that direction, pointed away. I also have an electric field due to this negative charge that's further away, so it's a little weaker, but it's pointed toward the negative charge. So I have two vectors pointed in the same direction, and they're going to add up, and they're going to point in that same direction. If I move a little further over, like I go right in between them, I'm going to have a vector a little weaker than I had when I was close to the positive charge, but still there pointed in the same direction, and a little stronger from the negative charge. Still there, so giving me still a vector in the same direction. And over here, I have a weaker still vector from the positive and a stronger one from the negative, still added, pointing in the middle. So our electric field in the middle is just going to be a line pointed straight over. They're just going to add up to each other, going out of this positive into that negative. Now that's just right in a straight line between them. What happens when we get out from in between them? So let's take a look at that. So let's go right here, let's say. Well, for here, if I look at this point, I've got a vector pointed along the field line away this way from positive. Pretty big one. From the negative, I have a little field, because I'm further away, pointed over towards it. Right? Pointed over in this direction. I didn't draw that very well. It's pointed over in this direction. It's a little vector pointed that way, toward the negative. Well, if I take these two vectors and I add them up, what I'm going to get is a vector not in line with either one of them, but slightly angled. Right? Slightly angled. Okay? Slightly angled off of what it was when it was just the positive charge. And then if I go to the next little part, I move over a little bit, like say right here, I've got a weaker one coming from the positive and a stronger one now from the negative, getting closer, and it's going to be another field line bent even more. It's like curved over even more. If I go between, it'll be the same amount from both, and the field will be horizontally over. And if I go over here, then the negative charge will start to win, and it'll be bent more pointed toward the negative sign. Negative charge. And as you get closer, the negative one dominates more and it points more toward it. So what shape is that? If you look at our little vectors we drew in, over here the positive charge wins, so it's mostly pointed in the positive charge electric field direction. In between it ties, so it goes in between this direction for the negative, for the positive charge, this direction for the negative charge. It goes in between them. And then as we get closer to the negative starts to win, and we get that kind of shape. And that shape is just going to be a field line that does like that. Bends over. And then the same sort of thing's going to happen here. This one's going to be affected by that negative one, so it's going to start to bend over, just not as much. And it's going to curve over like this. All right? And it goes out of the positive into the negative. This guy's going to be affected a little less, so he's going to just be curved kind of a little bit, maybe going off to infinity. Same thing over here. It's going to curve in, because it's going to be affected by that positive charge a little bit. This is just going to be weakened. It's not going to change its direction. Same thing with this guy. Okay? And then this guy, same thing on the bottom. It's going to curve. This is going to curve way over like that. We're going to have this other one curving in between. Out of the positive into the negative. And then this is out of the positive. And so we're going to get something that looks like this. If you notice, the electric field in between is stronger than it was. So I'm going to just real quick in yellow, I'm going to draw in. This is what it was before in this area. It was this. And these lines were further apart than they are here with the black lines, the yellow lines, right? This is what it was from that positive charge and from the negative charge. And so when we add these field lines, they added up like vectors, and now they're not crossing, and it's stronger in between them. They get closer together. Before, up here, these are pretty far apart. Now they're not as far apart because they're curving over. So in between it got stronger, but look out here. Out here it stayed like this. The field lines were like this. And so these were closer together than they are now. As this one curves away, it's gotten further apart, which means it's gotten weaker out here, and it's weaker out here, and it's stronger in between. Because in between they're adding up. On the opposite side, you think about this positive charge creates an electric field pointed this way out here. This negative charge creates an electric field pointed this way, the opposite way out here, right? Oops, I'm sorry. I said that backwards. The negative charge creates an electric field pointed into it over here, so to the left. The positive charge creates an electric field pointed to the right out here. It's smaller because it's further from the positive charge, but it still reduces it down a little bit because they're in opposite directions. They kind of cancel out. And so you get some kind of shape like this. What happens if you have two of the same charges? All right, so two of the same charges, so say two positives, right? Two positives. What will happen is, if you look at in between, this has a vector going this way, this has one going this way. So they're going to cancel out in between. So in between, it's going to basically be nothing. Well, what's going to happen up off of here? Well, up off of here, what you're going to have is one vector pointed this way and another pointed this way, and it's going to kind of result in it pointing upward. When it's closer to this one, when it's closer to the left side, it's going to be more dominated by the electric field coming from this one, so it's not going to be perfectly upward. It's going to be kind of slanted in this direction, and over here it's going to be more dominated by this one, so it's going to be pointed more in its direction. And the way we can write that is to simply do something like that, where they do this and they get closer and closer to vertical as you go up, right? Because over here, this part of the electric field is mostly going to be due to this positive charge, so it's going to be more in the direction of it, and it's going to a little bit affect it. But as you move closer and closer, further from this one, you get closer to this one, and they start to equal out, and you get a field line like that. And then the same thing over here. It's going to kind of curve it away, and curve it away, and curve it like this. And they're going to curve away from each other, like this. And hopefully you can go through kind of the point by point and think the way I did that last one about the way the fields would add up, what direction they're pointed, and how strong they are at each point. And you would see that you get something like this. The electric field is obviously weaker between them where they're canceling out. It's pretty strong around in here where they are both having a big downward effect on it. And then out here, you look, this one's creating an electric field pointed in this direction, this one's creating an electric field pointed in this direction, and it gets a little stronger. Because before, this field line would have gone like this, and out here, it would have been further apart, right, than here. Here, now they're this far apart instead of this extra distance apart. So it gets a little stronger out here, it's a little stronger around out here, and a little weaker right between them where it's canceling out. Okay, so that's drawing electric fields. There's one last thing to talk about in this video. Go through, practice drawing some of these, get used to those rules and everything, and that is conductors in electrostatic equilibrium. So what happens to them? So there's a few things that kind of tell us some rules. Most of this stuff you can actually derive out mathematically. We're going to try and kind of talk about it conceptually to figure this out. So let's start with just a conducting sphere. So it's a conductor, that means the charge is free to move. So even if this is a solid sphere, like a solid metal ball, if we put two positive charges, or let's say two negative charges, let's say we put two extra electrons in the middle. So everything's kind of neutral, but we put a bunch of, or not just two, we're going to put a bunch of extra electrons right in the center. What are they going to do? They're going to repel each other. They're going to want to get as far away from each other as they can, so they're all going to move out away from each other. Which means in order for them to get as far away from each other as they can, to get as far apart as they can, what you're going to have happen is you're going to end up with all of the negative charges, the excess charges, all those extra charges we stuck in the middle. They're going to want to go to the surface. They're going to spread out here and be on the surface. So our first little rule or property of them is that excess charge, so extra charge, resides on the surface. Okay, it all goes out to the surface to get spread out as far as it can. Secondly, and this is a consequence of rule number one, and you can actually learn how to actually produce this mathematically, but I'm going to do the kind of hand wavy just explanation here, is that the electric field, the E field, if you go inside, so anywhere inside it, not outside it, but anywhere inside the E field, inside is 0 everywhere. Everywhere, by everywhere I mean everywhere inside. So everywhere inside, the electric field equals 0, all inside of it. Why is that? Well, if you think about it, we have negative charges here. It's going to create an electric field pointed to the left, but all of these negative electric charges over here are going to create one pointed to the right. So you could imagine that these electric fields produced by the charges over here are going to cancel with the electric fields produced over here in between them. Much like up here when we had like charges, it kind of canceled out the electric field in the middle and made it 0. Well, here it's the electric field between two charges and between these two charges, and it's between all these like charges, and so it's going to cancel out to be 0 everywhere inside. Everywhere inside it, it's going to be 0. It's going to totally cancel out. And you can show that cancellation out, that it completely cancels out mathematically, but it requires, at least the way I know how to do it, requires vector calculus, which is essentially calculus 3. The third thing is that the E field is perpendicular to the surface at the surface. Now, as you move further away, this may not stay perpendicular because there could be some other charge out here that bends the electric field. But when you're really close, say we zoom in on this little spot here, let's zoom in, make it bigger, right? We're looking at the surface here, this curved part, here's the surface, and we have negative charges along the surface. Well, they each create electric fields pointed inward like this, right? And again, we're right between the charges here. And what happens to the electric field between like charges? It cancels out. So there's nothing in between them. And on the inside, we already said E was 0. E is 0 in between them. And the only place it doesn't cancel out, look here. As we go out further, look at these. These are all kind of pointed upward. They're kind of start to point in this direction, right? They curve and go straight out. With these electric fields, they're going to do that same sort of thing. They're going to curve and start to go straight out, perpendicular. But then you also have to add in the contribution from these other charges on the outside, not just these two, but these other ones. And it turns out that it all adds up to giving electric fields that at least near the surface, are leaving that surface perpendicular everywhere. They're leaving that surface perpendicular to it. Now again, if I have something like a positive charge over here, they're going to leave perpendicular and then they could curve over later. But right when they're leaving the surface, they're perpendicular, okay? Because they cancel out everywhere else, inside and in between. And then the last rule, and this one's a little harder to understand, and I don't know that I'm going to spend a lot of time trying to explain it here, but if we have something that is not the same shape the whole way through, right? And I'm going to leave it to kind of you to go through and think about this. Charge, and this one almost seems counterintuitive, charge accumulates, if it's not like a sphere where it's the same shape everywhere, accumulates at the sharpest points, where you have the smallest radius of curvature. So here, this end is sharper than this end, which means that you're going to get, if we put negative charges on it, they're mostly negative charges are going to kind of accumulate around where it's bent the most. I'm going to probably draw too many of those there, right? So here where it's flat, there's not going to be many charges. I drew too many here too, I think. Over here where it's curved, you're going to have a little more. Here where it's sharpest, you're going to get the most charges. And if you go through and think about it, when you get on this kind of thing, that field line's pointed out kind of radially out this way. So here at the sharp points, we can actually separate their electric field the most. Out here where it's flat, they're like right next to each other and they really kind of push each other farther apart. Over here, because the electric field between them is canceling out, they can't push each other as far apart in that direction, and so they kind of tend to accumulate on the sharper points. Okay? That's pretty much it then for these electric fields. I know I kind of went through it really fast, but I knew this was going to be a long video. Go back, watch over how we draw these again. Try and draw some different situations, like maybe where you have 2Q that's positive, like a bigger positive charge, and then a smaller half as big negative charge. what would the field look like between those two? Try and see if you can think your way through it. You can find the answer, I'm sure, somewhere in a book, in your book or online, right? Oh, these were two separate pictures. Okay, be sure you go through that. Try to understand what the electric field is, that it is this made up imaginary thing, but we're going to treat it as though it's a real thing. And in fact, something I forgot to say is if you look at this, the way I think about it is I think about it as though it's flowing water. And I think of positive charges as flowing water, that water just comes out of the faucet and flows out. And I think of negative charges as drains. The water just goes down the drain. And then if you put a charge in here, say I put a positive charge right here, it's going to follow the current. If I put a positive charge here, it's going to flow out along and follow the electric field line. I put a positive charge here, it's going to follow that electric field line, it's going to flow in. I put a positive charge here, it's going to follow and curve around and follow that electric field from the faucet down to the drain. And you could think if I had a faucet going in a drain that the water would flow in a pattern kind of like this. The only trick to this is it works really well for positive charges, but for negative charges, you have to think a little different, because if I put a negative charge here, it's going to flow in the opposite direction of the field. I'm going to put a negative charge here, it's going to flow away, because it's attracted to the positives and rejected by the negatives. And if I put a negative charge here, it's not going to flow around this way, it's going to go this way. It's going to go in the opposite direction of the flow. The only thing I can think of that kind of matches that is the salmon swimming upstream. They're going to want to go the opposite direction that the water is flowing for some reason. Okay, it's the only really kind of little sticky point in thinking about this as flowing water. The positive charges are just going to push along with the flowing charges. The negative charges are going to go in the opposite direction of the flowing water. Okay, so again, it's a really good model. It helps a lot. You just have to remember that one little tricky part is that the negatives are going to go in the opposite direction like salmon. Okay, I think that's pretty much it.